Good day, I'm Norman Wildberger. Today we're going to look at unique factorization, one of the most fundamental theorems in number theory. And we're going to be looking towards understanding this unique factorization for bigger and bigger numbers. And we're going to see that when we do that, the familiar certainty that we usually associate with this result starts to break down. We're going to see that there's actually serious difficulties with this theorem once we start turning our gaze to bigger numbers. So let's first of all get familiar with the standard formulation of this result. So it's a very famous theorem. It goes back to Euclid a long time ago. And the statement is that every natural number n can be written as a product of prime numbers in essentially a unique way, which means up to reordering of the factors. So for example, here's a couple of numbers. Here's 81,590, and its factorization into primes is 2 times 5 times 41 times 199. And if we look at the next number, which is 81,591, we get 3 times 27,197. That happens to be a prime number. The next one, 81,592, is 2 cubed times 7 times 31 times 47, and we see for the first time a prime appearing more than once, which typically can happen. The next number is product of 2 primes, 139 times 587, and then the next one is 2 times 3 cubed times 1,511. Okay, it's clear that this prime factorization, if there is some kind of pattern to it, it's not very obvious what it is. Although I guess we can see that there's some relationships. If this number here has 2 as a factor, then if we go 2 up, then we'll also get 2 as a factor, and so on. But predicting what these sort of bigger primes that appear here is quite tricky. But nevertheless, any one number can, according to this theorem, be factored uniquely into a product of primes. And this comes from Euclid's books, basically 7 and 9. So it's a very beautiful result, and of course, sort of a pillar of number theory. Well, there are 2 really important ingredients in this theorem: the idea of a natural number and the idea of a prime number. Well, let's suppose that we kind of understand what natural numbers are. For those of you who've been watching this series steadily, you're maybe not as confident about that claim as you might have been formerly. We've sort of touched base with the idea that natural numbers are actually quite complicated to define correctly. But let's suppose, for the sake of argument, that we are comfortable with the idea of a natural number. And let's remind ourselves about what a prime number means. Well, a natural number n, and for technical reasons we look at numbers n bigger than 1, is prime if it is not divisible by any natural number m less than it, which is also bigger than 1. So a number is prime if it doesn't have any factors less than itself, except for the trivial factor 1. Every number is divisible by 1. So verifying that a number n is prime is actually a lot of work, because according to the definition, you have to check that it's not divisible by every single number less than it, except for 1. That's especially a lot of work if n happens to be large. Okay, but for smaller values, it's not hard to find out what the primes are, and they're very familiar: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41. Well, let's carry on a little bit further. 43, then 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. Those are all the primes less than 100. Then 101 is prime. So is 103, 107, 109, 113, 127, 131, 137, 139, 149, jump of 10, 151, 157, 163, 167, 173, 179, 181, 191, another jump of 10, 193, just a pair there separating those, 197, 199, another twin prime pair. Then 211, a bigger jump, 223, 239, 241, we're seeing some little bit bigger jumps. 251, 257, 263, 269, 271, 277, 281, then 283, 293, 307, 311, 313, 317, 331, 337, 347, 349, 353, 359, 367, 373, 379, 383, 389, 397. Those are the primes less than 400. Okay, they of course carry on, and eventually we get to, say, 100,000 in that area there, and then sort of starting at 100,000, the primes are 100,003, 100,019, 100,043, 100,049, 100,057, 100,069, 100,103, 100,109, 100,129, 100,151, 100,153. And eventually, a little bit further on, we get up to, say, 10 million. And at the 10 million mark, the next prime is 10,019, and then 10,079, 10,103, 10,121, 10,139. Of course, keeps going. And it turns out that the millionth prime is this number here. The millionth prime is 15,485,863. So this pattern of primes has fascinated mankind for a long time. Okay, and it's interesting because it's kind of regular in a kind of way. They move up, never by wildly big jumps, but sort of smaller jumps and then bigger jumps, and it's sort of random. It certainly seems kind of random. But as the numbers get bigger, well, then the jumps do start getting bigger. There's more space separating adjacent primes, but still there's some kind of pattern, even though there's seemingly a lot of noise in this pattern. Okay, so it's a very interesting combination of regularity and irregularity. Very fascinating combination of those two things at the same time. It's what makes it perhaps so interesting. And of course the fact that these are the building blocks in this multiplicative sense because of the unique factorization theorem. These irregular things are the kind of atoms which are the constituents of all of the numbers. Now we're particularly interested in the logical structure here because that's the problematic issue here. So we really want to understand why is the theorem true and what possible difficulties might there be with this theorem. Okay, so the theorem has two parts. There's a statement about existence of a prime factorization for a natural number, and there's the statement of uniqueness up to order of such a factorization. So let's start with the existence. Given a natural number n, well, we want to explain why we can factor it into primes. If n is prime itself, then we are done. Then this is a factorization and we can stop. Otherwise, it means that n is divisible by some number less than it. So it has a factorization of p times q, where p and q are numbers less than n. I mean, any factors of n have to be less than or equal to n. And if p is bigger than 1, then q has to be less than n. So these two factors have to be between 1 and n, strictly between 1 and n. Okay, and now if p and q are primes, then this is a factorization and we're finished. Otherwise, we continue. We take one of them. If it's a prime, no problem, then we go to the next one. So if they're both primes, then we're done. But if one of them is not a prime, then that one can be further factored. And we just keep on doing that. The process must end at which point we have a prime factorization. So it must end because the numbers involved are getting smaller and smaller. They're natural numbers, and each factor is smaller than the number that we're starting with, but still bigger than 1. And that's a finite process which eventually must stop. This is often stated in terms of induction. So it's a little bit subtle, but I think we could all sort of see what the argument is. The uniqueness part of the theorem is a little bit more subtle, even to state and also to prove. So if n has 2 prime factorizations, let's say n is equal to p1 times p2 times all the way up to pk, so we have k primes, and n is also equal to the product q1 times q2 all the way up to ql, where we have another, say, L primes. So if these are both prime factorizations of n, then what do we mean by the uniqueness of the prime factorization? Well, we can say it very efficiently in terms of multisets. We can say that the multiset consisting of the primes p1, p2, all the way up to pk, equals the multiset q1, q2, all the way up to ql. So this is a multiset that contains each one of the factors here exactly once. So the p1 is there, the p2 is there, all the way up to the pk is there. There can be repetitions here because there can be repetitions in the prime factors here. But the ordering here doesn't matter. The order here doesn't matter. So the multiset framework is exactly what we need to capture the aspect of having multiplicities as well as not being ordered. So it's a lot more awkward to say this without m-sets. Okay, now to prove that this is true, it involves showing that, say, p1, the prime that we start off there, actually equals one of the qi. That's the standard way of showing that these two things are these two multisets are the same. We choose one of these primes, let's say p1, and then we're going to convince ourselves that this prime that we've taken from the first factorization actually agrees with one of the primes in the second factorization. It's the basic argument. Once we've done that, so let's say we've decided that p1 happens to be equal to, say, q7, okay, then we can remove the p1 and the q7 from both sides, and then we have two smaller factorizations, and then we repeat the process. Basic idea. All right, I want us to go through and have a general idea of the direction of this proof. So in order to prove that equality of m-sets, we need to show that if p1 divides this big product of primes, q1, q2, all the way to qn, that it actually equals one of those primes. And the key ingredient for that is this innocent-looking lemma called Euclid's lemma, which is that if p is a prime and p divides a product of two natural numbers, n times m, then either p divides n or p divides m. So for example, 17 is a prime. 17 happens to divide 335,257. And you can check that this number actually is the product of 481 times 697. Okay, so Euclid's lemma applied to this situation would allow us to deduce that since 17 divides this product, that therefore it must be true that 17 either divides 481 or it divides 697. One of those has to be true if it's true that 17 divides the original product. And I'll let you decide which one of these is the case. It's interesting and useful to contrast that with the example where we're dividing by something that's not a prime. So here's a situation where 18 happens to divide 136,422. And this number is the product of 159 times 858. Okay, but we are not allowed to deduce that 18 either divides this or this. So it turns out that 18 does not divide 159, and 18 does not divide 858. Okay. So here is the lemma being applied correctly to a prime, and here is a example of the lemma not working because the number that we're dividing by is not a prime. Euclid's lemma is relatively simple, but it's a little bit subtle, and it's sort of the basis upon which this argument that if P1 divides a product, then P1 actually equals one of the primes rests on. So the heart of the matter is convincing oneself that Euclid's lemma is true. All right, so we're investigating a little bit of elementary number theory here, pretty well found in any kind of number theory text. But we want to move a little bit in this direction. So we're going to be talking about number theory a little bit. But with the aim of looking at number theory for bigger and bigger numbers, which is a little bit interesting and maybe a little bit unusual. Okay, so how do we prove Euclid's lemma? Suppose that P does divide the product n times m, and P is a prime. All right, so if P divides the first number n, then we are done. What we're trying to do is deduce that P either divides n or it divides m. So if P divides n, well, we can finish. So otherwise, we can say, well, then if P does not divide n, then, well, we want to make a deduction and eventually deduce that P divides m. That will then prove what we want to do. All right, so if P does not divide n, what does it mean? It means then that P and n are relatively prime. That's often indicated by this symbol here. And I remind you that relatively prime means that they have no common factors. P is a prime, and P does not divide n, then we can conclude that P and n have no common factors. Why is that? Well, it's because P is a prime, and it only has two factors, namely 1 and itself. It's not divisible by any other number in between 1 and itself. So it only has two factors, 1 and P. So if P and n have any common factors, they're either going to be 1 or P. But we've decided that P does not divide n, so P cannot be a common factor between P and n. So the other possibility is that 1 is the common factor. All right, so if P does not divide n, we deduce that P and n are relatively prime, or they only have a common factor of 1. And now, this implies an interesting relationship between P and n. This relationship is called Bezout's identity. And it states that we can find numbers r and s such that r times p plus s times n equals 1. And what are these r's and s's? Well, they're some integers r and s. So we're stepping outside the bounds of what we've been talking about up till now. We've just been talking about natural number arithmetic. Now we're invoking some integers. R and S are possibly integers. So Bezout's identity claims that if P and N are relatively prime, then we can find integers R and S such that R times P plus S times N equals 1. Now if you'll accept this for a moment, then we can complete the proof of Euclid's lemma. And it goes as follows. We take this result here and we multiply both sides by the other number m. So we get RPM plus SNM equals m on the right-hand side. And now we look at this and we say, okay, P, our original prime, divides RPM because obviously there's P there sitting as a factor. And P also divides this product S times NM because we're assuming that P divides NM. So P divides this product here, so it certainly divides the product of S with NM. So we're in the situation where P divides this and P divides this, and therefore P must divide the sum of those two things, which is M. So we've deduced that P divides M. Right, so the structure of the argument is we assume that P divides the product NM, If p is dividing n, we're fine. Otherwise, we invoke Bezout's identity, getting these r's and s's that satisfy this particular relation, do the trick of multiplying by m, and deducing that therefore p must divide m. And that's Euclid's lemma. And so now if we have Euclid's lemma, well, then this unique factorization kind of works, because then P1, well, it divides the big product of Q's. So then you split that big product into Q1 times all the other ones. And then we know that P1 either divides Q1 or it divides the big product of the other ones. If it divides Q1, then it must actually be equal to Q1, because two primes one can't divide each other unless they're actually equal. And if it doesn't divide Q1, well, then it has to divide the other product, and then we apply the same procedure until eventually we get P1 dividing one of the Q's, and then that must be equal to that Q. Okay, so there's an argument, but it's basically an extension of Euclid's lemma. You can see that the story is somewhat subtle, and that Euclid must have been rather a genius to put it together, and it's very much the case, right? This is 300 BC, where this was really very well understood. Okay, so maybe Euclid's argument is a little bit different from this, but we still have to talk about why this particular identity is true that we've invoked here, and that's also of independent interest. So there's a little bit more to the story. Examining where does this thing come from. All right, so Bezout's identity is named after Etienne Bezout, who lived from 1730 to 1783. And it is, I'll state it again, perhaps in different language, if we have two numbers a and b and they're relatively prime, they're natural numbers, then Ra plus Sb equals 1 for some integers r and s. We can find some linear combination of a and b that will equal 1. So for example, 9 and 17 are relatively prime. They have no common factors. So let's find an r and an s so that when we multiply 9 by r and 17 by s, the total is 1. And we're going to do it in this sort of systematic way that also goes back to Euclid. We're basically going to divide. This is the division algorithm of Euclid. So let's take the bigger number, which is 17, and divide it by the smaller number, which is 9. So if we divide 17 by 9, we get a quotient of 1 and a remainder of 8. 17 divided by 9. And now let's take the 9 and divide it by the remainder, 8. 9 is equal to 1 times 8, plus now a new remainder of 1. And now let's play the same thing. We'll take this last thing we divided by 8, and we'll divide it by the new remainder. 8 is equal to 8 times 1 with a remainder of 0. This thing here then is the last non-zero remainder before we got a perfect division. And it's at this point here that we can reverse the steps to find the r and the s. So we're going to take this formula and then we're going to massage it using also this formula to get r and s. So here's how that works. So here's this formula here, and we're going to rewrite it down here as 9 minus 1 times 8 equals 1. I'll keep the 1 times just sort of for reference to keep things organized. Here's a formula that expresses 1 as a combination of 9 and 8. We're going to replace that formula by getting rid of the 8 from the previous line. So from this line here, we can write this 8 as 17 minus 1 times 9. So I'm going to replace this 8 here with 17 minus 1 times 9 from here. Now I have a formula, 9 minus 1 times 17 minus 1 times 9 equals 1, that only involves multiples of 9 and 17. And if we look how many 9s do I have, well I have 9 there once, and now we have minus 1 and a minus 1, altogether plus 1 there. So altogether we have 2 9s minus 1 times 17. So we deduce that 2 times 9 minus 1 times 17 equals 1, which we probably could have figured out relatively easily anyway, but this sort of just illustrates the general technique in a somewhat simple example. So in this case, the r would be the 2, and the s would actually be minus 1. So 2 times 9 plus minus 1 times 17, if you like. That combination equals 1. Let's have a look at a slightly more sophisticated example. Let's look at the two numbers 26 and 19. These are also relatively prime. They have no common factor. So according to Bezout, we can find r and s, which are integers, such that r times 26 plus s times 19 combine to give us 1. Now this has an amusing geometrical interpretation that I want to share with you, okay, which sort of shows that this problem is of independent interest other than just factoring numbers. It has actual applications that are a little bit interesting. So imagine here we have a line with little steps. Okay, there's one step separating each of these little notches. And suppose that we want to go from here, circled in red, to the adjacent notch 1 over. So there's the start and there's the finish. That would be pretty simple in ordinary terms because we would just take one step to the right. But suppose that for some reason or another we are not allowed to take just one step and we're constrained to take only big steps. In fact, we're allowed to take either a step of 19, so we can take a step of 19 in either direction, or we can take a step of 26 in either direction. So we can always take a step of either 19 in either direction. We can always take a step of 26 in either direction. If we could only take steps of 19, well, clearly we could only get to multiples of 19, positive or negative. But since we're allowed both multiples of 19 and multiples of 26, it seems at least plausible that we might be able to get from here to here. And that's what this is actually asserting. It's asserting that we can find a certain number of 26 steps, which when followed by another number of 19 steps, will total just a step of just 1. Okay, so how do we do this? How do we find these r's and s's? Well, we start by dividing. So 26 divided by 19. We'll divide the bigger one by the smaller one. So 26 is 1 times 19 plus a remainder of 7. And then we're going to divide 19 by 7. 19 is 2 times 7 plus a remainder of 5. We've just divided by 7. Now we're going to divide 7 by the remainder. So 7 is 1 times 5 plus 2. The next step, we take what we divided by, 5, and divide it by the remainder. 5 is 2 times 2 plus a remainder of 1. We divided by 2, so we'll take that and divide by the remainder. 2 is 2 times 1 plus 0. The last non-zero remainder is 1. That's in fact, the greatest common divisor of these two numbers. This is an actual algorithm that, if you just choose two general numbers, will generate the greatest common divisor of them. But we're going to take that last equation and then we're going to work our way back up. So we're going to start with this equation involving 1 as a combination of 5 and 2's. And we're going to kind of work our way up until we have 1 expressed as a combination of 26's and 19's. So let's see how that goes. So we've just copied that there. And then we're going to take this 2 that appears here and use the previous equation to replace it with 7 minus 1 times 5. So this 2 is replaced with 7 minus 1 times 5. Now if you look at this and you don't actually multiply it out, you just think in terms of multiples of 5's and 7's, then altogether we have a 5 here and plus 2 5's there for a total of 3 times 5 minus 2 times 7 equals 1. And we can check that that's true. 15 minus 14 is 1. So we've expressed 1 as a combination of 5 and 7. Now we want to move up to a combination of 7's and 19's. So what we're going to do is we're going to replace this 5, which is the previous one, with what we get from this equation. From this equation we see that 5 is equal to 19 minus 2 times 7. So this 5 here gets replaced with 19 minus 2 times 7. We still have the minus 2 times 7 over here, equals 1, of course. And then when we stare at this, we see that we have combinations of 19s and 7s floating around here. We have 3 times 19, and how many 7s do we have? We have minus 6 7s there, minus another 2 7s, for a total of minus 8 7s. So 3 times 19 minus 8 times 7 is 1. That's 57 minus 56. Yes, that equals 1. We're still doing something correctly. Now at the final stage, we're going to remove this 7, replace it with 26 minus 1 times 19. So that 7 gets replaced with 26 minus 1 times 19, and now hopefully there will only be 19s and 26s in this equation. So we see that there's 3 times 19 there, and how many 19s here? There's minus 8 times minus 1, so there's plus 8 19s for a total of 11 times 19. So maybe right here, 11 times 19. And we also have minus 8 times 26, that's all, minus 8 times 26, and that equals 1. So there we have expressed 1 as a combination of 19 and 26. So I guess in this language here we could say r is equal to minus 8, and I guess s equals 11 if I've done the arithmetic right. So if you want to get from here to there, one step to the right, then you should take 8 steps of 26 to the left, go left with 8 big 26 steps, and then add 11 19 steps, and then come back with 11 steps of 19, and then you will end up right there. You see, this kind of would have industrial applications. If you have some kind of robot arm that can go 26, or another robot arm that goes 19, and you have to maneuver these robot arms to move something from here to here, well, you have to figure out something like this. Okay, so this illustrates how Bezout's identity is justified, and Bezout's identity is then the ingredient that makes Euclid's lemma work, and Euclid's lemma is then the ingredient that essentially makes the unique factorization work. And that's a rough outline of the story, the usual story for the theorem of Euclid, the unique factorization. Everything certainly seems to be hunky-dory. But I'm suggesting that maybe everything is not hunky-dory. That contained in this story, there's some potential difficulty. And that's exactly what happens. So there is some potential difficulty. But that potential difficulty only becomes really visible when we move beyond our comfortable zone of small, familiar numbers, and we head out to bigger numbers, like Z. Okay, so I claim that Z does not have a unique prime factorization. That by the time we get to Z, this argument somehow has broken down. And so we want to examine that claim. We want to have a look at it. Is that possible? How could that be? What part of the argument might not work for such a big number, or relatively big number, as Z? We're going to investigate that next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.